Ever since Werner Heisenberg's 1927 paper on uncertainty, there has been considerable hesitancy in simultaneously considering positions and momenta in quantum contexts, since these are incompatible observables. But this persistent discomfort with addressing positions and momenta jointly in the quantum world is not really warranted, as was first fully appreciated by Hilbrand Groenewold and José Moyal in the 194H. While the formalism for quantum mechanics in phase space was wholly cast at that time, it was not completely understood nor widely known, much less generally accepted until the late 20th century. When Feynman first unlocked the secrets of the path integral formalism and presented them to the world, he was publicly rebuked. It was obvious, Bohr said, that such trajectories violated the uncertainty principle. However, in this case, Bohr was wrong. Today, path integrals are universally recognized and widely used as an alternative framework to describe quantum behavior. Equivalent to, although conceptually distinct from, the usual Hilbert space framework, and therefore completely in accord with Heisenberg's uncertainty principle. The different points of view offered by the Hilbert space and path integral frameworks combine to provide greater insight and depth of understanding. Similarly, many physicists hold the conviction that classical valued Positian and momentum variables should not be simultaneously employed in any meaningful formula expressing quantum behavior, simply because this would also seem to violate the uncertainty principle. See Appendix Dirac. However, they are also wrong. Quantum mechanics QM can be consistently and autonomously formulated in phase space, with a number position and momentum variables simultaneously placed on an equal footing, in a way that fully respects Heisenberg's principle. This quantum framework is equivalent to both the Hilbert space approach and the path integral formulation. Quantum mechanics in phase space QMPS thereby gives a third point of view which provides still more insight and understanding. What follows is the somewhat erratic story of this third formulation. The foundations of this remarkable picture of quantum mechanics were laid out by H. Weyl and E. Wigner around 1930. But the full, self-standing theory was put together in a crowning achievement by two unknowns, at the very beginning of their physics careers, independent of each other, during World War II, H. Groenewold in Holland and J. Moyal in England. See Appendix Groenewold and Moyal. Their theory was only published after the end of the war under considerable adversity and in the face of opposition by established physicists, and it took quite some time for this uncommon achievement to be appreciated and utilized by the community. The net result is that quantum mechanics works smoothly and consistently in phase space, where Positian coordinates and momenta blend together closely and symmetrically. Thus, sharing a common arena and language with classical mechanics, 14 QMPS connects to its classical limit more naturally and intuitively than in the other two familiar alternate pictures, namely, the standard formulation through operators in Hilbert space, or the path integral formulation. Still, as every physics undergraduate learns early on, classical phase space is built out of a number, position coordinates and momenta, x and p, ordinary commuting.